we have a section to cover today, but the good news is it's a very quick section, at least it was the previous class. So we're going to do chapter 4.2, and that will be the 6th topic that you'll be doing for your test. And your test is on Tuesday, as you should know. So there's not an awful lot to the Rolle's theorem. So some people just get a little bit confused in the sense that it almost feels like you haven't done anything, but you are answering a question. What Rolle's theorem said is, imagine that you have a function that starts at x equals a, and it finishes at x equals b. And it's a nice continuous function, right? So there's nothing weird going on. And you can differentiate to everybody. And it has one last property, that the value of the function at the start is the same number as at the end. If all of those properties are true, then Rolle's theorem says there must exist at least one number C and it has to be in the intervals between A and B. So C has to be somewhere between A and B, such that the derivative at that number C will be 0. So what it says is, say if you've got a continuous nice function that's differentiable, and it starts at this height and then it finishes at that height, isn't it kind of guaranteed that there's at least going to be one place where the derivative is 0? In this particular case, there happens to be 2 of them, right? I mean, the logic of it kind of makes sense, right? If you start at this height and you finish at this height, and you have to go from one place to the other, and you have to do it as a continuous value, don't you have to curve? And if you curve, won't you make a 0 derivative? You might make it 2 or 3 places, but Rolle's theorem says that you must at least, it must happen at least in one location. So for Rolle's theorem to work, the function has to be continuous, CTS for short, and differentiable, DIF, diff n for short, in the interval A to B. And the value of the function at A has to be the value of the function of B. So if all of this is true, Rolle's theorem says there must exist at least one number C between A and B such that the derivative at C is 0. I guess you could say it in English, there must be at least one hill or a valley, right? There's no way of avoiding it. Well, I guess you could say, well, couldn't I just do a straight line from A to B? Well, technically you could. And if you did that, wouldn't the derivative still be 0? There'd just be an infinite number of places where it was 0. So even in that weird situation, Rolle's theorem still works. So what do most of your questions look like? Well, they give you a function, apart from the first 2 questions, and they ask you to use Rolle's theorem. So I'm going to jump right in with this guy. Here is a function, and we are interested in using Rolle's theorem between -4 and 4. Would you agree that this function is continuous and differentiable? Can we just take that for granted? We don't need to prove something that's as obvious, right? Would you agree it's just a normal polynomial and all polynomials are continuous? Now, the value of the function at the start is the value of the function at -4. And you're going to trust me, it ends up being -61. And the value of the function at the end, which in this case is 4. And again, you're going to trust me, ends up being -61. And isn't that the second part of Rolle's theorem now verified, right? I've verified that it's continuous and differentiable because it is. And now I've checked that the value of the function at the start and finish are both the same. in this case, negative 61. So far, so good. So what we're going to do now is find the mysterious c. So you find the derivative of the function. So that's 3x squared, take away 8x, take away 16. And you solve for when is it 0. This quadratic factors. Anybody know what the factors for 3x squared minus 8x take away 16 are? Two numbers that multiply together give you negative 16, but when you FOIL it all out, you get negative 8. There is a combination that works.
Is it negative 4 and 4?
As long as you put them there, yes. And that means that one of the solutions could be negative 4/3, and the other solution could be 4. And the way that WebAssign gets you to write the answer is that these numbers are called C. So here's a little thing that might catch you. Negative 4/3 is in that interval. Stick it in the box. If I was allowed to use 4, I do comma 4. But Rolle's theorem only says that. Do you notice that you can't use the endpoint? Now you might say, well, the endpoint works here, but the theory goes and says, look, you can't be sure that at the endpoint something is differentiable. So just don't go there. So we are just going to pick that guy and ignore that one. Now, suppose I'd had a second answer and it was x equals 2. Wouldn't I've put it in there? Suppose the second answer was 12. Why won't I use 12?
It's not in the interval.
It's not in the interval, right? So if it's not in the interval, you can't use it. If it's on the boundary of the interval, you can't use it. If it's inside the interval, use as many guys in the interval as you've got, right? So if you've got 2 or 3 answers, they're all good, as long as they're in the interval, not in the boundaries, and not outside. So in a funny sort of way, we didn't do much there, didn't we? Essentially, aren't we just finding when the derivative is 0? And the rest is just a preamble for why we're allowed to do it.
So
that one,
negative 4 not work as well?
Correct. It's on the boundary, so you can't use it. By the way, that was a version of question 3. Let's try another Rolle's theorem one. Okay. This is question 5. It's a quadratic. Would you agree that that quadratic is continuous and differentiable? Let's find the value of the function at the beginning, which in this case is -1. And then we'll find the value at the end, which in this case is at 3. Okay, if you plug in 3, you get, what do you get if you plug in -1? You get 3, 7, 13. So we'll do 13, yep. Rolle's theorem can now be used. So we are going to find the derivative, which in this case is 6x take away 6. And according to Rolle's theorem, because this is a continuous and differentiable function, and it starts and finishes at the same place, there's guaranteed to be a 0 derivative. And that ends up being 1. And would you agree that 1 is the only solution and it's in the interval like it was promised? And so we can stick in that in our box. Would you agree Rolle's theorem is mostly about finding when derivatives are 0? Now, let's show you a situation where you cannot use Rolle's theorem. Here's a function and we're interested in -8 to 8. That function is actually continuous. If you plugged into a calculator, it works totally fine. Hasn't a problem. It has a kind of weird shape to it. It kind of comes round and goes like that. But it's continuous. I'm going to find its derivative, which is basically multiply by the power and then reduce the power by 1. And I'm going to just make it slightly pretty with style points. Is there a problem with this derivative at any value of x at all? Because I can tell you one value of x where there's a problem.
Am I seeing a vertical in the middle?
I'm not hearing, you're breaking up, so I'm not quite sure what you're saying.
Am I seeing a vertical line in the middle of that?
Yeah, you are. And what's happening to the derivative at 0? Isn't it infinite? That's why you're seeing a vertical line here. So would you agree that the derivative is not differentiable at 0? Differentiable means you get a number. You can't get infinite. It doesn't count. So it's not differentiable at 0. So that means you can't use Rolle's theorem. And if you tried to find some place where the derivative is 0, it does not exist. So DNE. So not all functions have 0 derivatives, right? And this function failed because its derivative had a problem at 0, and that destroyed Rolle's theorem from working. Now, just because Rolle's theorem doesn't work doesn't mean that there might not be places where the derivative is 0. Right? But if it isn't usable, you shouldn't be using it. Let's do this one. Still on Rolle's theorem, the function we've got looks like there could be a problem. Is this function continuous? Well, let's talk about it a different way. Where does this function have a problem? Where is it not continuous? There's only one place where it has a problem.
0.
But 0 is not in that interval. So isn't this function okay? Because between here and here, there isn't a problem. Now, if I differentiate this function, you eventually get that. Does this derivative have a problem? Yeah, it has a problem at 0. But is 0 in my interval? No. So isn't this function continuous and differentiable as long as you pick values of x between 1, 6, and 6? It would have a problem if you said, I know, -1 to 1, right? Then you'd have problems and Rolle's theorem couldn't get used, but Rolle's theorem is okay. We only worry about the interval. What's going on in this interval? Outside that interval, it can be the ugliest looking function with all sorts of problems. But as long as inside that interval, it's cool, it's good, Rolle's theorem is your friend. Now, if you find the value of the function at the start, which is at 1/6, and you find the value of the function at the end, which is at 6, you get 6 1/6 in both cases, which we all know should be called 37/6. So according to Rolle's theorem, is the start and the finish the same height? Yep. That means Rolle's theorem is in operation. Continuous, differentiable, and the start and finish are at the same height. So that means there should be some place where the derivative is 0. There should be some place where the derivative is equal to that. we've got to solve for x. God, there's I got about 3 different ways to solve this. Do you know what the answer is just looking? That would count as one of them. What values of x can you use that makes this answer on the left 0?
Positive or negative 1.
Yep, that would be one method. Second method could be to multiply both sides by x squared and factor as a difference of 2 squares, in which case you'll get that -1 and x equals 1. Another possibility would be to add that to both sides to do a cross multiply and to get plus or minus 1, say. Well, there's probably another, if I thought about it, I could probably come up with another way of getting the answer. You know, it doesn't matter which one of those you get as long as you get -1 and 1, right? As long as you solve it. And then you're going to make this mistake if you're not careful. Hopefully you won't. You're going to say, oh, there we go. 2 places, I'm done. And WebAssign is going to say you're wrong. Which one of those 2 guys do I have to kick out?
-1.
Because it's not in the interval. So the real answer, in this case, happens to be just one number. So to kind of recap, Rolle's theorem says that if you have a nice continuous differentiable function whose height at the start and whose height at the end are the same number, then it is guaranteed that there's a derivative somewhere that's equal to 0, and you should be able to find that x coordinate, we call it c, and that's essentially the question over. And that's Rolle's theorem, named after a guy called Rolle, I strongly suspect. So here's the theorem that's named after the chapter. It's called the mean value theorem. And what the mean value theorem is, essentially, is imagine you've got a nice continuous differentiable function, but more realistically, it starts at A and it finishes at a different height B, which is what you'd expect most of the time, right? It's kind of unusual to start and finish at the same height. It can happen, but it's pretty unusual. Isn't it more likely you start at one and you finish at a different height, which is what that's trying to represent. Now, if this function is continuous and differentiable, just like Rolle's theorem, right? That's restriction. The mean value theorem says the following. There will exist at least one number c in the interval from A to B, right? Somewhere between here and here. There's guaranteed to be at least one number such that the derivative at C is the same thing as this expression. And this expression is actually the average slope from the start to the finish. Okay, imagine you draw a line from the start point to the finish, right? This green line. The rise and the run are these guys. So in English, what that says is that if you have a continuous differentiable function, there's at least one point on that curve that has the same slope as the average slope, right? The average slope from A to B. Rolle's theorem is actually just a special case of that. If f of A equals f of B, doesn't that just give you a 0 value? So Rolle's theorem says the derivative is 0. So actually the mean value theorem is the generalized version of what Rolle's theorem says. So how do you apply it? Well, you pretty much just do what we do in all situations. We check out that you're allowed to use it, and then we find C. So let's take a function that doesn't have an awful lot going for it, a nice quadratic, and it starts at 0 and it finishes at 2. Would you agree that this function is continuous and differentiable? Just because it is, it's pretty obvious. Now, I'm going to find the average value from the start to the finish, right? The average slope. That's A and that's B. So in this case, it's f of 2 take away f of 0 over 2 take away 0. And the value of the function at 2, that's 2, 4, 20, 20. Take away 4 over 2 take away 0. And the answer I get is 16 over 2. You get 8. So according to the mean value theorem, MVT for short, there is guaranteed to be a place where the derivative is 8, the average slope. Now, the derivative of this function is 10x take away 2. That becomes 10x is 10, and that ends up being x equals 1. And the place where this happens is guaranteed to be between 0 and 2. And would you agree that 1 is bang in the middle of 0 to 2? And in Weber sign, they call that number C. So C equals 1. So instead of you finding when is the derivative 0, the mean value theorem says you're now going to find when is the derivative equal to the average slope. Are we good with that? Okay, got notes. I like notes. Let's do a version of 11 then. Right, here is a cubic equation, and we're interested in it between -2 and 2. Can we just assume that it's continuous and differentiable? Because it is. We just don't need to prove it. I don't think it's self-evident. Let's find the average between these two places. So it's going to be the value of the function at 2, take away the value of the function at -2, over 2, take away -2. Right, the value of the function at 2, 2, 4, 8, 8 take away 6 is 2, you get 11. The value of the function at -2, that's -8, add 6. Wait a minute, is that the same guy? That would be annoying. -2, no, it can't be. 2, 4, 8, 17 take away 6 is 11. Okay, that works. -8, that's 1. Okay, it's 7. And you get 4 over 4, so you get 1. So the average slope from the start to finish is 1. Then according to the mean value theorem, you're guaranteed to find a place where the derivative has a slope of 1. And that's 3x squared take away 3 is 1. That's 3x squared is 4. That's x squared is 4/3. And that makes x plus or minus the square root of 4/3, which is plus or minus 2 over √3. And both of those are inside the interval. So we can have -2 over √3 and +2 over √3. So there's actually 2 places in this curve that have a slope of 1. Let me show you how the math behind this is used in a very practical way. Britain, I'm sure in America as well, has problems with people speeding on the motorway. Britain is much more lax, I can tell you that, than America is. The speed limit in motorways, right, the highest legal speed you can go is 70 miles an hour. But in Britain, nobody gets a speed ticket for doing 80. In fact, if you do 70 on a motorway, people beep the horn at you because you're holding up traffic, right? So 80 mile an hour is what you would get in a motorway. But they don't like people going over that, right? For very obvious safety reasons. And what they used to do, you imagine the motorway, you know how you have those bridges from time to time that roads go over, right? Overpasses, I think you call them, right? They used to put speed cameras on them. And as your car went by, the radar got your speed, right? And it took a picture of your license plate, right? And what happened there was that if you were doing over the speed limit, you know the ones you get at traffic lights, they do that right now, don't they? They do a little radar-y thing, they get your picture, and you get sent a speeding ticket, right? That was working until people started doing this. They started knowing where the speed cameras were. And so they would travel along the motorway at 90 or 100 miles an hour. They would come to that bridge and they'd slow down to a 70 mile an hour. Once they were by that, they then zoomed off for the next 5 or so miles till they got to the next speed camera at 100 mile an hour or 90 mile an hour. And then they would slow down to 70 mile an hour again when they went over the speed thing. And then off they went. So they'd done this, speeding up, slowing down, speeding up, slowing down. So they could never get a speeding ticket. So being sneaky, the government changed what these cameras did. They didn't take your instantaneous speed as you went over the overpass. They took a timestamp of where you were. And they took a timestamp of where you were. This is a fixed distance. The bridges don't move. They did an average speed between the two flyovers. If your average speed was over the speed limit, in other words, was this number bigger than, say, 80 mile an hour, then didn't you have to at least once break the speed limit to get an average speed of 80 miles an hour? So you get sent a speeding ticket. So you see that you can use calculus to catch speeders. And it was essentially the mean value theorem trick to do it. If your average speed is 80, you must have been doing 80 sometime. Even if you can argue, well, I was doing 70 mile an hour here and I was doing 70 mile an hour here, they're going to say that doesn't matter. Your speed was 80 on average. So somewhere between here and here, you were breaking the speed limit. You had to. There's no way you could have avoided it. I think that was kind of interesting. So let's do another one. Let's do a log one. This is version 12. A log function from 1 to 3. Now, is the log function continuous? Phrase it a different way. Where's the problem with the log function? Because it does have a problem. What value of x does the log function have a problem?
0.
0. It doesn't have a vertical asymptote at 0. It's bad news, right? What about the derivative 1 over x? Where does it have a problem? 0. But aren't we only interested in 1 to 3? So isn't this function okay? It's continuous and differentiable as long as you're only using values of x between 1 and 3, right? 0 is not there, so it's not a problem. So this function is continuous and differentiable. The average value, or the average slope, is this guy. So it's f of 3 take away f of 1 over 3 take away 1. So it's a natural log of 3 take away the natural log of 1 over 3 take away 1. Let's see if we can catch it out here. What's the value of the natural log of 1? What's the number?
0.
Yeah. So the average slope of this function between 1 and 3 is this guy. So according to the mean value theorem, there is guaranteed to be at least one place where the derivative is equal to that guy, right? Now the derivative is just 1 over x, which is that guy. Agreed? Okay. Without any hard work, tell me what x is. Should be easy to figure out what x is without doing too much work.
2 over natural log.
Yeah, just reciprocal or reciprocal, right? Turn it back upside down. You'll have to trust me, but do you know 2 over log 3 is a decimal, but that decimal is somewhere between 1 and 3. I guarantee it, right? So there's your answer. Where on this curve do you have a slope that's the same as its average? When the x-coordinate is 2 over log 3 is where that will happen. That's what the mean value theorem is stating. We're going to leave this right now because that's pretty much it. There are a couple of questions at the beginning which are really just to do with looking at pictures and explaining the mean value theorem or Rolle's theorem. So hopefully those are pretty easy. And that is the end of that section. So I want to now spend what time we've got left talking about your test. Right, we all know that Monday is a holiday and that the test is on Tuesday, right? I'm 99% sure I said it at least once, right? So it's not a shock to you. What we're looking at here, if I make it just a little bit bigger, there. Oops. Are the topics for test 4. There are 6 topics, but the test is only going to have 4 questions. That means 2 of these topics will not appear in your test. According to Murphy's Law, isn't it the 2 that you didn't study for that are going to be in the test? So you will make sure that you study all the topics because you don't know which one is and which one is not going to be in your test. The section 310 is covered in the extra credit video. I've extended that extra credit video now until midnight Monday, so you can still get an extra 2%. And even if you don't do the questions and get that 2%, you really should watch the video if you want to know how to do the homework. So make sure that you know how to do linear approximation and differentials, because it may or may not be in the test. And the mean value theorem also may or may not be in the test, and so is any of the others. Quick summary: log and inverse trig functions. That was the first one. Remember what the derivative of a log is, but couldn't you also do a thing called logarithmic differentiation? Like finding the derivative of x to the power of x, that kind of thing. And really didn't do that much on inverse trig functions, but you know, if I do an ABC, I could certainly ask you to do that. Well, let's put you to a test. Anybody here know what the derivative of an inverse tan function is?
One over x squared plus 1.
Nailed it. Anybody know what the inverse sine function is?
What's that?
The inverse sine function, what its derivative is. Starts with a 1 over. Square root.
1 over the square root of 1 plus minus x squared.
Yep. And the inverse cosine is the same thing, but a -1 rather than a +1 at the top. Right. Not a lot in the inverse trig functions, but I guess if you got a chain rule, it might make it a little bit harder. Then we have the rates of change, which are basically derivatives, velocity, acceleration, rocks going up and hitting the ground, you know, those kind of questions. Related rates, those horrible formulas where all the variables are in terms of t. Remember the aircraft flying and the radar station and what was it, v equals 4/3 pi r cubed, and the guy with the shadow walking away from the lamppost, those questions. Linear, right? Well, how you can find a linear approximation to a function. Absolute max and mins. Remember critical numbers, testing the two endpoints in all the critical numbers. The biggest one is the absolute max, the smaller is the absolute min. And what we do today, mean value theorem. Usual rules apply, don't cheat. There's going to be a Zoom meeting. Anything that's written down you can use. WebAssign will disappear during the test. Everything on Canvas will disappear except the test, the place to upload your work into, and Desmos will be there because you can use Desmos to, you know, help you when you want to sketch things. I didn't mention this to my other class. I'm going to have to, but it came to me right now. You know that there are 5 tests, but only the best 4 count. So some of you might get a break. If you do really, really well in your first 4, can't you just opt not to take the 5th test? Because I take the best 4 out of 5. Now, if you've done really bad in a test, you better take test 5. Well, you actually better do good in test 4 as well, but you better take test 5 to at least improve your grade. So for some of you, that might mean you get a little break. You get a day off when we do the last test. Any questions, or are we good?